So we're ready to look at determinants in a little bit different light. We talked about cofactor expansion. Now I want to talk about finding determinants using row reduction. A couple preliminary things I just want to state before we move on to looking at how essentially elementary row operations affect the determinant. The first is that if we have a square matrix A, and A has a row or a column of zeros, then the determinant of that matrix must be 0. So based on cofactor expansion, that should make sense. If you have a row or a column of zeros, if you do cofactor expansion along that row or column, clearly you're going to get 0. Remember, cofactor expansion is taking every entry in, say, the row and multiplying it by its cofactor. But if all the entries are 0, right, then we're just going to get a sum of zeros. Same thing along any column. So that's an important observation. Another thing is maybe needs a little more explanation, but seems feasible. If we have a square matrix A, then the determinant of that matrix is equal to the determinant of the transpose of that matrix. Now we're talking about square matrices here, of course, only when we talk about determinants. And why would this make sense at any rate? Why would the determinant of a matrix be equal to the determinant of its transpose? Remember, the transpose is what? We've basically interchanged the rows with the columns, right? Interchange the rows with the columns. And so if you think about it, for matrix A, its determinant is found by cofactor expansion along, say, any row. Well, any row of A corresponds then to what? A column of A transpose. And so we're finding the determinant along a column over here. And so you can see why the determinant would be the same. Now, there is a little bit of a mixture when you're looking at the corresponding minors for those entries. They kind of get scrambled a little bit, and so the proof of this is a little bit more in detail, but this certainly seems feasible here, since we can do cofactor expansion along any row or column and get the same result, right, the determinant of the matrix. It kind of makes sense that this works. So I want you to remember this fact, that the determinant of any matrix is equal to the determinant of its transpose. Okay. So with that, then, let's look and see how row operations affect the determinant of a matrix. And I'm not going to prove these. I'm going to illustrate them with simple 2x2 matrices. So let's start with this general 2x2 matrix. We know what its determinant is, right? AD minus BC. And then I'm going to create matrix B by swapping the rows of B. Right? So I'm just swapping, interchanging rows 1 and 2. So what's the determinant of this new matrix? Well, now it's what? CB minus what? DA or AD. Okay. But then think about this. I can rewrite this if I wanted to as negative AD plus BC. All right, CB is the same as BC. And then I can factor out a negative 1 from this, and I'm left with negative 1 times what? AD minus BC. Aha. And we recognize that as the determinant of the matrix A. And so this illustrates the following. If B is obtained in general from the n by n matrix A by interchanging any two rows of the matrix A, then the determinant of B is going to be what? Negative 1 times the determinant of the matrix A. So by interchanging rows, we essentially change the sign of the determinant. Okay. And again, this is a illustration. It's not proving it. We only shown it true for a 2x2 matrix, but it is true for n by n. Okay. Next row operation, let's look at how multiplying a row by a non-zero scalar changes things. Okay. So we have a matrix A. We're going to create B by multiplying, in this case, row 1 by K. So I multiply row 1 by K, I get this matrix B. So what's the determinant now? It's Ka times D minus KBC. And if I factor out a K, common factor, I'm left with, again, AD minus BC. So this illustrates the following fact. If B is obtained from the n by n matrix A by multiplying a row, in fact any row, by K, then the determinant of B is K times the determinant of A. Okay. Well, now let's go to our last row operation. What kind of crazy relationship are we going to get here if we add a multiple of one row to another? Oh boy, that's crazy, right? Take this 2 by 2 matrix, create B, and this time I'm going to add K times row 1 to row 2. K times row 1 added to row 2. So KA added to C gives me C plus KA. KB added to D gives me that. So here's the new matrix. Well, let's see what the determinant is here now. It's A times D plus KB minus B times C plus KA. Okay. Well, let's clean this up a little bit. I'm going to distribute the A through and the B through, the negative B through. So I get AD plus A times KB is KAB. I'll write it that way, KAB. And then minus what? B times C, that's minus BC. And then minus B times KA, that's minus KAB. And what do you realize? KAB minus KAB, that's 0. And I'm just left with AD minus BC. Whoa. Do you see what this illustrates? If B is obtained from the n by n matrix A by adding K times any row to another row, then the determinant of B is equal to what? The determinant of A. It's not affected. We get the same thing, and that's pretty crazy. Anytime I add a multiple of one row to another, the resulting matrix, the determinant of that resulting matrix is the same as the matrix we started with. So these are the 3 row operations and how they affect the determinant, right? Interchanging 2 rows essentially changes the sign of the determinant. Multiplying a row by K does what? K times the determinant. And then if I add a multiple of one row to another, the determinant is not affected. The determinant of the new matrix is the same as the original one. Now, I just want you to observe the following as well. These observations that we made are true not only for row operations, but column operations as well. Now, we haven't done really column operations per se when we're doing Gaussian elimination or the inversion algorithm, right? We're doing row operations. But here it says if we replace row with column, we get the same results. In other words, interchanging any 2 columns of a matrix, the determinant changes sign. Multiplying a column by the constant K, the new matrix is K times the determinant of the old matrix. And if I add a multiple of one column to another, it doesn't affect the determinant. The determinant is the same. Okay, and you can actually prove that fact right there, just like well, at least illustrate that fact just like we did with the row operations. Okay, with that, I want to take a look at the elementary matrices. What is the determinant for elementary matrices? Well, we know that if we have an elementary matrix, results by performing one row operation on the identity matrix. Okay, since we know the determinant of the identity matrix is 1, how do I know that? How do I know right off the bat that the determinant is 1? Because the identity matrix is a diagonal matrix with 1s all down the main diagonal. And remember, any triangular matrix, or which a diagonal matrix is, the determinant of any such matrix is the product of the main diagonal entries. So a product of n 1s is, of course, equal to 1. So the determinant of identity is 1. But this leads to the following. If we have E is an elementary matrix n by n, if E results from interchanging 2 rows of the identity matrix, then the determinant of that matrix is -1. Why is that? Because remember, when we multiplied, when we interchanged any 2 rows, what did we say? The determinant changes sign. So the determinant was 1, now it's -1. If E results from multiplying 1 row of the identity matrix by the non-zero number K, then the determinant of E is equal to K. And that's because, remember, we just showed that if I multiply any row by K, it's going to be K times the determinant of the previous matrix, or the one we obtained it from. K times 1, of course, is K. And if E results from adding a multiple of one row of the identity matrix to another, then the determinant of E is, of course, 1, because the determinant is unaffected. Okay, so an important fact here is to note that for elementary matrices, their determinants are always non-zero. They're either -1 or 1 or K. And remember this K, when we're doing row operations, then we usually say what k is non-zero, right? If we're solving a system of linear equations, we can't multiply both sides of the equation by 0. So in general, when we talk about elementary matrices, their determinants are all non-zero. Here's a theorem which I'm going to state without proof here, but we'll talk about the proof. If A is a square matrix with 2 proportional rows or 2 proportional columns, then the determinant of A is 0. So what are we saying? What are proportional rows or proportional columns? Proportional rows means that one row is just a constant multiple of another row. So for instance, I could have one row being A, B, let's just say, for my first row, and my second row would be like KA, KB. Right? So maybe I have 2, 4, and then here I have 4, 8, 2, 4, 4, 8, where K is 2. So they're in proportion to one another. Why would this matrix here have a determinant of 0? How do we know that? Well, because in one row operation, I can create a row of zeros, right? I can take negative k times row 1 and add it to row 2, right? If I do negative k times row 1 and add that to row 2 and replace row 1 with that result, then what do we get here? We would get A, B, 0, 0, right? So how does that affect the determinant of this matrix going from here to here? Adding a multiple of one row to another. Well, we just said it does not affect the determinant. So the determinant of this matrix is the same as the determinant of this matrix. And so what do we know about the determinant of any matrix that has a row of zeros? It's 0, right? The determinant is 0, cofactor expansion along that row. And so we can see why this theorem is true. If we have 2 proportional rows or 2 proportional columns, and the determinant of that matrix is 0. Now, we're ready to start playing around with the idea of using row reduction in the process of finding a determinant. And one of the things I want to look at is this idea of factoring out a scalar from a row or column and its effect on the determinant. So what is the relationship between the determinants of the following matrices? Okay, well, let's first of all ask, what's the relationship between these two matrices? Okay, we see the second and third rows are the same, but the first rows are different. Can you think of a row operation that was done in going from here to here? Sure. Right, going from here to here, we did what? We have basically what? Row 1 is multiplied by 1/3, right? So 1/3 row 1 is replacing row 1, right? Going from A to B, all right? So if I was doing, like if I was doing row reduction, if I was trying to put this in reduced echelon form, the first thing I want to do is get a leading 1 here. So it kind of makes sense that I would do that, right? There's my leading 1, okay? So when we do that, though, we say what I want to do is if I want to find the determinant of this matrix, we know that doing this row operation doesn't affect anything, right? I'm sorry, it does affect the determinant, right? Because of this multiple of 1/3, right? But I want to keep track of this in a certain way. And so in going this way, of course, I'm multiplying row 1 by 1/3. But in going back in this way, what would be happening? I would be multiplying row 1 by 3. Right? That would be the inverse operation. So what is the connection here then? Since this matrix A can be thought of as being obtained from B by multiplying row 1 by 3, then the determinant of this matrix A is what? 3 times the determinant of this matrix B. Okay? That's the relationship. So I want to emphasize this because it's a little confusing. And when we're doing row reduction in going from this matrix here, matrix A, to matrix B over here, we would think of multiplying row 1 by 1/3. But when I look at the determinant of this one compared to the determinant of the new matrix, determinant of our matrix is 3 times this one. So the tendency is to put a 1/3 there. Okay, and so it's a little confusing when we're doing reduction how that works. But here's a way of thinking about it that works as well, and that is I can think of across this row of factoring out a 3. If I factor out a 3 out of any row, that can come out, right, as a sort of a constant multiple times the determinant. Remember, these are determinants, right, because I've got the vertical lines here, right? These are real numbers, determinants of these matrices. But if I factor out this 3, then we can think of it that way. And I can do it along any row or any column. If I find any common factors, I can pull them out, so to speak. And so that's sort of the one little tricky thing about doing the row reduction. Let's take a look and see how we can do a couple of these here. What can we factor out of any row or column here to simplify this determinant? Well, the second row here, clearly there's a factor of 7, so I can pull that 7 out. And this would be what would be left? 7, 1, 4, 2. Okay. You could also factor out of a column. Notice here in this column there's a common factor of 5, so I can factor out that 5, and what's left? 3, 11, 6, and this is what? 1, negative 5, 3. Okay, so that's sort of the idea behind simplifying when we do row operations, and I'm going to illustrate it here in this case. So let's take a look at using row reduction to evaluate a determinant. So one thing we could do is let's try and put this into row echelon form. And as we do so, let's keep track of how the determinant is affected by those row operations. And the reason, once I get it in row echelon form, by the way, row echelon form is a triangular matrix, and I know how to find the determinant of any triangular matrix. So the determinant of matrix A, I'll just write this, can be written this way. And the first thing I'd like to do is get a leading one here, right, to get this in row echelon form. Well, in order to do that, I can't multiply by any constant to get this to be 1. I need to do what? Interchange, right? I need to find a non-zero entry below the 0. So let me interchange rows 1 and 2. Okay. If I interchange rows 1 and 2, I get this matrix. So again, this is interchanging rows 1 and 2. Do you remember how that affects the determinant of the matrix? How does that affect the determinant matrix if I interchange rows 1 and 2? Remember, the new determinant is -1 times the determinant of the previous one, and so we can multiply this determinant by -1 and we get the same relationship. Okay. Now what do? Well, I need this to be a 1, so how do we do that? Typically we do what? Take 1/2 row 1 and replace row 1 with that. So that gives me, if I divide everything by 2 here, 1, 3, -1. These are all the same. Okay. But then how does that affect this? So we still have this -1 out here. Don't forget that. How does this, do we put a 1/2 here? No, remember the idea when we're going in this direction. Think of it almost like what? Factoring out that 2. Factor out that 2. It comes out here as a 2, right? And so that's the tricky thing. So again, if you think about it, this matrix, right, related to this one here, well, you can think about going from here to here, we can multiply row 1 by 2 to get to this one. So the determinant of this one is 2 times the determinant of this one. That's what we were saying when we multiply, right? And so be very careful how that works. If you say you take this matrix, multiply by 1/2 to get this one, then it's 1/2 times this determinant equal to this determinant. But you see, if that's the case, then this has to be 2 times this determinant. So the best thing to think of is think about that factoring out when you're doing the multiplying a row by a non-zero constant. What do we need now? We need zeros beneath our 1. Here's a 0 here. I need to get a 0 here. So how do I do that? I need to get a 0 for this. I'm going to take row 3, and I'm going to add what? Negative 3 times row 1. And I'm going to replace row 3 with that result, right? That's going to get the 0 there. Let's go ahead and do that operation. Only row 3 is going to change here. So negative 3 times 1 added to 3, that gives me 0. Negative 3 times 3 is negative 9. Negative 1 plus a negative 9 is negative 10. Negative 3 times negative 1 is positive 3. 1 plus 3, that gives me 4. There's the new matrix. Right. Now how does that affect things? Of course, this product here is negative 2. How does that affect things when I add a multiple of one row to another? How are these determinants related? Well, they're the same. Remember, if I add a multiple of one row to another, there is no effect on the determinant. No effect on the determinant. And finally, then, how do I get rid of this 10? You say, well, first of all, I need to get a leading 1 here, and then I can, multiply the pivot 1 by 10 and get rid of that negative 10. But in this case, I see, hey, I can just add 5 times row 2 to row 3, and I can zero this out. And I'm going to do that. Take row 3 and add 5 times row 2 to get what? So 5 times 0 added to 0 is 0. 5 times 2 is 10 added to negative 10 is 0. 5 times 1 is 5 added to 4 gives me 9. Okay, so I am not quite getting this in row echelon form, and that's okay. Don't forget I still have this negative 2 down here times the determinant of all this. Notice here I could get ones, leading ones if I want to, but I'm not going to do that. I'm simply going to note, hey, I now have a triangular matrix. I have an upper triangular matrix, right? What's the determinant of any triangular matrix? It's the product of the main diagonal entries. So this is 1 times 2 times 9. And so our determinant becomes negative 2. 2 times 9 is 18. I get negative 36. Okay, so the idea is, that we try and get the matrix into a form where I can find the determinant easily. That could be putting the matrix in row echelon form. It could also be introducing, if it's a real large matrix, introducing a bunch of zeros. We know if there's a lot of zeros in a row or column, that's helpful. And notice that's pretty cost free in terms of how that affects the determinant, because every time I'm getting zeros, I'm typically doing what? Adding a multiple of one row to another. How does that affect the determinant? It does not. And so there's no hard and fast rule about how row reduction can be used to find the determinant of such a matrix. Often it's a little bit of an art form, you could say. There's lots of things we could do, but a typical thing again is to put it into a row echelon form, as I've done here, and then use that, or into at least a triangular form, and then use that triangular matrix, right? Then what you know about the determinant of that to find the determinant of your original matrix. Okay. Sometimes you could use a combination of the two. You can sometimes get it to this form, and then you can do a cofactor expansion to find the determinant. Because again, this process is very good for introducing zeros, cost-free, so to speak. Let's look at this little example here. Find the determinant of this matrix B. Okay. And you say, it's going to be a pretty long process of putting this into its row echelon form, because we've got a lot of stuff over here, right? We do have some zeros though, so if I was doing cofactor expansion, I would probably choose this third column, right, to expand around. But if you look at this very carefully, you'll see something that we could do. Remember, we talked about the fact that not only can we do row operations, But we can do column operations now when we're talking about just the determinant. We can't do them for solving systems of linear equations. Can't do that to the augmented matrix, column operations. But we can when we're looking at the determinant of a matrix. And what I want you to see is I want you to compare columns 1 with columns 4. Do you see anything interesting? What if I take column 4 and add -4 times column 1 to it and replace column 4 with that, adding a multiple of one column to another? How will that affect the determinant? It won't, right? So the determinant of B would be equal to the resulting matrix determinant when I do this operation, because it doesn't affect the determinant. So the determinant of B would be the same if I do that. How does column 4 affect it? Well, let's recopy the first 3 columns. And what happens when I add -4 times column 1 to column 4? Well, -4 times 1 is -4 added to 4, that's a 0. -4 times 2 is -8 added to 8, that's 0. -4 times -4 is +4 added to 16, that's 0. -4 times 0 is 0 added to -5, well, that's -5. But look what we have here. In one step, what have we done? We don't have an upper triangular matrix, we have what? A lower triangular matrix. What is the determinant of a lower triangular matrix? Same as for an upper triangular matrix. It's the product of the main diagonal entries. And so this is now just the product of these main diagonals entries, and we get the determinant sort of in one step. So you can see if it's sort of an art form. If you accidentally, or not accidentally, but if you actually see that relationship, you can save yourself a lot of time. Okay, you can save yourself a lot of time. So again, this is not the only way to find the determinant, but again, this is a quick way to do that. So when you're doing row operations or column operations, when you're doing row reduction, column reduction, you can use these ideas to help you find the determinant matrix. And it'll be a lot less costly than just brute force doing cofactor expansion. Even though you go along this column here, you still got 2 non-zero entries, and for each one you have to compute a determinant of a 3x3 matrix, right? The minor would be 3x3. Okay, in closing, let's just take a look at put all the stuff that we've learned in this section together. Suppose I have a 3x3 matrix, square matrix, and I know its determinant is 4. Then let's find the following determinants. And so look at this one. Compare it to the matrix A. What's the relationship between this and matrix A? Clearly, rows 2 and rows 3 have been swapped. And so the determinant of this matrix is what? -1 times the determinant of matrix A. Remember, if we interchange 2 rows, then the new determinant is -1 times the determinant of the previous one. And so the determinant of A is 4, and so this is -4. What's the relationship between these two? Well, clearly we've taken 2 times row 2 and added that to, or replaced row 2 with that. So what is that? How does that affect it? Well, multiplying by the constant k is k times the original determinant. So it's 2 times determinant of A, 2 times 4 is 8. What about here? A, B, C, D, E, F, the same. This row is different, and we can see then what? This was row 3 added to -3 times row 1. And how does that affect the determinant? It doesn't. The determinant is the same. Remember, when we add one multiple, we'll add a multiple of one row to another. The determinant is unaffected. Okay, so you can sort of do these sort of things given this information. Look at this one here. Compare it to A. So A, B, C, D, E, F. D, E, F, A, B, C. So first of all, I know I've swapped rows 1 and rows 2. And so that net effect is what? -1 times the determinant of A, as we did previously. But I also have what? -3G, -3H, -3I. So I've multiplied row 3 by -3. So I did 2 row operations here. And that does what? -3 times what? -1 times the determinant of A. So what's the net effect? I'm going to multiply by +3. 3 times the determinant of A is the determinant of this matrix. Remember, the determinant of A was 4, and so 3 times 4, this is 12. If I look at this one, notice ABC, that's the same as the first row, but then I've got D plus 3A, E plus 3B, F plus 3C. So this is row 2 plus 3 times row 1, replacing row 2 with that. But how does that affect the determinant? It doesn't. Notice here I've got G minus 2 times A, H minus 2 times B, I minus 2 times C. So this is row 3 plus what? Negative 2 times row 1. And again, no effect, right? So I've just did 2 row operations, but they don't have any effect on the determinant, so it's the same. The determinant of A is 4, and so the determinant of this matrix will be 4. Keep in mind, I am not going to try and calculate the determinant in terms of A, B, C, G, H, I, D, E, F, all those letters, right, in any of these cases. I'm using them, comparing it to what I know already. Okay. How about this one? Compare this one to the previous one. Remember, it was ABC in the first row, now ABC is in the second row. DEF was in the second row, now it's in the third row. And GHI was in the third row, now it's in the first row. So we've done basically what? 2 row swaps or 2 row interchanges. So one way of doing it is interchange rows 1 and rows 2, right? That is going to affect us negative 1 times the determinant of A. And then I would have to do row 2 with what? With row 3. So swap row 1 and row 2, and then swap row 2 with row 3. So if I do row 1 and row 2, I get ABC here and DEF, and then row 2 with row 3 gives me, whoops, did I do that right? Let's see. Row 1 with row 2 would give me DEF up top and ABC in the middle, and then I want to swap 1 and 3. Sorry, 1 and 3. Sorry about that. So you might want to write those out. So in other words, we swapped 1 and 2, so ABC came down here and DEF came up here, and then we swapped GHI and DEF rows 1 and 3. Sorry about that. So this affects it as negative 1 again, and so the net effect, of course, is what? Negative 1 times negative positive 1. It's just the same as the determinant of A, which was 4. So doing 2 row interchanges is going to get us right back to the same determinant. All right, take a look at this one. Instead of row operations, notice we've done some column operations. Okay. So the original matrix was in first column ADG, BEH, CFI, and notice BEH and ADG were swapped. All right, so the first and second columns were swapped. Which is negative 1 times the determinant of A. And then we did what? 2 times column 3. How does that affect things? 2 times, right? The determinant. So the net effect is negative 2 here. Negative 2 times the determinant of A, negative 2 times 4 is negative 8. And our last example then is, what's the determinant of A transpose? Do you remember from the beginning of the video what we said about that? Determinant of A transpose is the same as the determinant of A. And so that's just 4. Okay. So I really like these type of questions. We'll do some more as we look in the next set of lecture videos about properties of the determinant and see how we can continue to look at this. And then hopefully we're going to come back to this question in the next set of lecture videos, and that is, what about a square matrix that is invertible? What can we say about its determinant? And that'll be very important for us, and we'll learn that in the next set of lectures.